All right, so on to the next lecture. It says week 2, but we're still in week 1. But what we want to do before we go any further, we covered with the first lecture unity of life, the characteristics that all living things share. Talked about scientific method. But before we go into any further biology, we want to pause and talk about some basic chemistry. Because we'll talk about some things we'll touch on for the rest of the semester. All right, so we just want to cover some of those here. All right, so what is an atom? An atom is, or atoms are the building blocks of all matter. All right, and you can break an atom down into subatomic particles. All right, and those are protons, neutrons, and electrons, and those particles make up an atom. A charge is an electrical property. All right, and opposite charges attract. So protons have a positive charge. Electrons have a negative charge. Those charges can attract. All right, but so protons, positive charge. The neutrons they have a neutral charge, so they don't have a charge at all. And if you see here, so here's an example atom. All right, well, in the middle is what's called the nucleus of the atom. All right, and so in the nucleus is where you'll find the protons and the neutrons. All right, and then circling the atom's nucleus are the atom's electrons. Okay, so protons positive, neutrons neutral, electrons negative. The protons and neutrons are in the nucleus, and the electrons are move around the nucleus. Now, the atoms can differ in the number of subatomic particles. All right, so they can differ in the number of protons, the number of neutrons, and the number of electrons. All right, and so and those differences are how we classify different atoms. Okay, so the atomic number is the number of protons in the atomic nucleus, and it determines the type of atom or element. Okay, so the atomic number is the number of protons in the atomic nucleus, and it determines the type of atom or element. All right, and so elements are atoms that have the same number of protons in their nuclei. All right, so and those elements are organized in this periodic table. Okay, all right, and so in here you see the number 5, see number 6, number 7, number 8. That refers to the atomic number. Then you see here 10.811, 12.011. That refers to the atomic mass. All right, so the atomic number, this number here in the top left corner, all right, refers to the number of protons in the atomic nucleus and determines the type of atom or element. So all atoms that have 6 protons in their atomic nucleus are considered carbon atoms. All atoms that have 7 protons in their atomic nucleus are considered nitrogen atoms. All right. It would be helpful to go ahead and know the symbols for carbon, nitrogen, hydrogen, oxygen. Let's see, sodium, okay, which is Na, potassium, which is K, and then calcium, which is Ca right here. All right, those are major biological atoms or elements that you'll talk about over and over again, and not only in this class but other classes. So it's just helpful to go ahead and memorize those symbols. Okay, and so atomic mass is the total of all the subatomic particles. Okay, so protons, neutrons, and electrons, but the electrons weigh so little that it's basically the sum of all the protons and neutrons. All right, so that's the difference between, so know the difference between atomic mass and atomic mass and atomic number. Atomic number refers to the number of protons in the nucleus, and that determines the type of element that the atom is. All right, whereas the atomic mass is the sum of the protons and the neutrons in the atom, in the atomic nucleus. Okay. All right. So again, so here you have the periodic table. You have the atomic number. You have the symbol, and you have the atomic mass. Okay. All right. So then we get into this idea of isotopes. All right. So what are the differences, or what does it mean to be an isotope? So isotopes are the same elements, but they differ in the number of neutrons. Okay, so they're the same elements. All right, so here you have 3 examples. So you have carbon 12, carbon 13, carbon 14. They're all carbon. So what does that tell you? That all 3 of these atoms have 6 protons in their atomic nucleus. So how do they differ? They differ in the number of neutrons. So basically, this has 6 protons and 6 neutrons. This has 6 protons and 7 neutrons. And this has 6 protons and 8 neutrons. All right. Then you get radioisotopes. So radioisotopes have an unstable nucleus that breaks down spontaneously, and as it breaks down, it emits radiation in the form of particles, energy, or both. All right, and that process of that radioisotope breaking down is called radioactive decay. All right, and so that process happens at a predictable rate. So this radioactive decay process happens at a predictable rate, and it results in predictable products. So whenever you have carbon-14 undergoing radioactive decay, it always breaks down to nitrogen-14. All right, now I just threw this in just for your information. Don't really worry about this, okay? All right, but you can use different radioactive decay of different radioisotopes for different things, okay? Because they have a predictable rate of decay. All right, and so here you see, scientists can use carbon-14 to date the age of different things they find, let's say a fossil, right? Because they can measure the amount of carbon-14 that's in that specimen and be like, hey, we know that it's broken down at this predictable rate, so this means that this specimen that has this amount of carbon-14 and nitrogen-14 has to be this old. Okay. So carbon-14 is a popular radioisotope dating atom, and you see some here, and they have different half-lives. Again, a predictable rate of decay, all right, in different dating ranges that are useful for scientists to age different things. Okay, don't worry about memorizing this. Again, just for your information. All right. Another thing that radioisotopes are important for is in medicine. Okay. So isotopes have the same chemical properties, so organisms use isotopes of the same element in the same manner. Okay. And so because of that, radioisotopes can be used as tracers. So tracers are substances that have a detectable component. They are delivered into a biological system, and they can be followed through that system with instruments that detect radiation. All right, so here you have a PET scan of someone who was giving a tracer, and as it flowed through this person's body, all right, it was able to be detected by a PET scan. All right. Unfortunately, all these red things that you see in images are cancerous tumors. Right. So they're used in cancer imaging. They're used to diagnose heart disease. They're used to diagnose different conditions in the brain, such as dementia. So they're very important in medicine. All right. So let's kind of get back to the subatomic particles. All right. So again, protons and neutrons are in the nucleus. Electrons are in outside the nucleus in these shells. All right. And then you have the electron charge, or the electric charge. Sorry, proton being positive, neutrons being neutral, and the electrons being negative. All right, so let's talk a little bit more about electrons. So electrons carry energy. All right, the electrons are moving fast around the nucleus, but they never collide. They're kind of going within these different orbitals, and those orbitals have different energy levels. All right, and the orbitals that are further away from the nucleus have higher energy levels, and those electrons that are in those outer energy levels are called valence electrons. Okay, an electron can move to a higher energy orbital if some energy input gives it a boost. All right. When that boost in the atom occurs and that electron is pushed up to a higher energy level, all right, that electron then immediately emits that extra energy and moves back down to the energy orbital. All right, so the big takeaway point here is that electrons can carry energy between these different orbitals and release it. All right, then when we're talking about electrons, we need to think of this rule of 8 or octet rule. So atoms of elements important in life tend to gain, lose, or share electrons so as to have 8 electrons in their outermost energy shell. Okay. All right. Now the exception is hydrogen, which has 0 or 2 electrons in its most stable forms. All right. That gets to this idea of shell models. The shell model helps us visualize how electrons populate atoms. All right. And so basically their nested shells correspond to successively higher energy levels. And each shell includes all of the orbitals, okay, on one energy level. So you have the only shell that is not like the others is the first one. Okay, so the first shell can only carry a maximum of 2 electrons. All right, then after that, the second, third, fourth, and so on and so forth can all carry a maximum of 8 electrons. And like we said, that for an atom to be sort of considered stable, they want to have a complete or a full outer shell. Now, sometimes that may be they are wanting to receive electrons, and sometimes that means they are wanting to donate electrons. They want to give it away. Okay, so here's an exercise. So do the shell models, all right, based on the atomic number for hydrogen, helium, carbon, oxygen, nitrogen, sodium, and chlorine. Okay, practice those, and then I will upload kind of the answers to my Talladega. All right, but here's the key here, which I haven't mentioned yet. So how do you know how many electrons these things have? look at the atomic number. Okay, because for these things that right now they're not carrying a particular charge, that means the number of electrons and the number of protons have to equal one another. Okay, so for example, here you have carbon 12, okay, has an atomic number of 6. Okay, so that means you have 6 protons, and it doesn't carry a charge, an overall charge. So if you have 6 protons, how many electrons do you have to have? You got to have 6. Okay, so you can look at the periodic table, look at the atomic number, all right, and know how many electrons total should be in your shell model. All right. So, for example, we'll go back. Hydrogen. Okay. All right. It has has an atomic number of 1. So how many protons does it have? Has 1. Okay. And I want you to draw hydrogen with no overall charge, the shell model for that. So how many electrons does hydrogen have? 1. Okay. All right. So again, this idea of the octet rule, shells, atoms want to have a complete outer shell because unfilled vacancies make atoms more likely to react. All right, and so free radicals or unstable atoms are groups of atoms with unpaired electrons that can react readily with other atoms. Okay, and then ions are atoms that typically exist with uneven number of protons and electrons and thus carry a charge. All right, so we'll stop there, and I'll pick up with part 2 on this slide.